Okay, let's dive right into this. Welcome to today's Explainer. We're exploring a seriously fascinating breakthrough in artificial intelligence today, and it's called chain of code. We're going to see exactly how researchers are taking the fluidity of human language and merging it straight into the rigid precision of computer computation. The ultimate goal? Making AI models significantly smarter.
Now, you might be wondering, why do brilliant AIs struggle with basic logic puzzles? I mean, it's a huge paradox, right? We've all seen large language models write these beautiful essays, summarize massive documents, or literally draft an email for us in a matter of seconds. But then, they completely stumble when asked to do simple math or exact symbolic operations. It's honestly like having a brilliant philosopher in the room who suddenly just forgets how to calculate a restaurant tip.
So, let's look at Section 1, the AI reasoning problem, and why a new approach is needed. To really understand why standard prompting methods hit this wall, we have to look at the two main tools we've been relying on. Over on the left, we've got chain of thought, or CoT. You can think of CoT as the brain. It uses natural language to break down problems step by step, making it fantastic at semantic reasoning, understanding context and deep meaning. But for exact math, yeah, it definitely falters. Then on the right, we have program of thoughts, or POT. This is essentially the calculator. It actually generates code to solve problems, which means it's incredibly precise with numbers. But if the problem has any semantic ambiguity, any of those little nuances in the human language, it just crashes. It's really hard to encode meaning into strict code. So basically, neither method can do both. Which brings us to Section 2, Enter Chain of Code, the ultimate hybrid. So what is this ultimate hybrid? Well, Chain of Code, or CoC, is a framework that brilliantly merges the best ideas from both of those previous approaches. It actually asks the AI model to generate a program that mixes actual, executable code for all the hard math, along with semantic placeholders for those more nuanced language tasks. It literally bridges the gap, combining precise code execution with flexible, language-based reasoning. And now, to make this whole thing work, researchers introduced the LMulator. That's a language model-based simulation module. But what does that actually mean for us? Well, basically, when our calculator gets confused by a piece of code it can't execute because it requires human-like judgment, the LMulator steps right in. It uses language-based reasoning to simulate what the output should be based entirely on the context. It's the AI's brain stepping in to help its own calculator when it gets stuck. Let's jump into Section 3, how CoC actually works. Now, what's really interesting about this two-step process is how clean and highly structured it is. Step 1 is code generation, and Step 2 is code execution, specifically featuring our new best friend, the LMulator. Let's break these down. All right, starting with Step 1, code generation. When given a problem, the AI model writes out a step-by-step program. But listen, it's not just standard programming. Sure, it contains executable components like loops and arithmetic, but the real magic is in those semantic placeholders we talked about. The AI inserts these clever custom functions, like, say, isFruit or getCountry, precisely for those exact moments that are going to require human-like intuition a little bit later on. And then we move right to Step 2, code execution. This is where the live tag team happens. The code runs line by line. Your traditional code interpreter handles the precise calculations without even breaking a sweat. But the moment it hits one of those semantic placeholders, a line it can't traditionally execute, the LMulator tags in. It simulates the expected output for that ambiguous line, feeds the results straight back, and the program state just seamlessly updates. It's amazing. Let's move to Section 4, counting fruits with CoC, and see how this builds when we apply it to a practical example. Consider this exact riddle from the source material. It goes, I have an orange, a violin, 2 peaches, an apple, a pepper, and 3 plums. How many fruits do I have? Now, if you just used a standard code interpreter here, it would flat out fail. A standard computer program doesn't inherently know if a violin or a pepper is a fruit. It completely lacks that semantic judgment. But look at how chain of code handles it. The generated code sets up a loop to count the objects, using a semantic function called isFruit. The second the code hits that function, the LMulator takes over. For the orange, the LMulator simulates true, but for the violin, it acts as the brain and correctly outputs false. Peaches, true. Apple, true. What about the pepper? While botanically complex, in a common-sense everyday context, the LMulator flags it as false. Plums, true. It determines all these values based purely on context and feeds them right back into the running code. And because the LMulator perfectly handled all the semantics, literally separating the fruits from the instruments and vegetables, the code interpreter can just do what it does best: basic math. It safely sums up the counts for the true values. So 1 orange plus 2 peaches plus 1 apple plus 3 plums, giving us the correct final answer, 7. The code executed the structure, while the language models simulated the meaning. Let's wrap up with Section 5, the future of AI reasoning, and look at the broader implications here. And this brilliantly illustrates where we are right now. Looking at the landscape of AI prompting techniques, we have chain of thought, program of thoughts, and scratchpad. And as we've seen, they all have missing pieces, but only chain of code, right there at the bottom, gets a yes for both executes code and handles non-executable steps. It is uniquely positioned as the only method successfully handling both raw execution and semantic simulation at the exact same time. So, why does this matter for you? Well, chain of code is perfectly suited for complex tasks that mix heavy math with everyday common sense reasoning. It's incredibly adaptable to logical operations and messy data processing. And most importantly, experiments show it significantly outperforms traditional methods in benchmark accuracy. Basically, it makes AI models noticeably more reliable across complex, real-world challenges. Of course, every breakthrough has its hurdles, right? Running both a code interpreter and an LM simulator naturally requires more processing overhead. That makes it inherently slower than just asking an AI for direct text-based reasoning. Plus, some super abstract tasks are still pretty tricky to simulate accurately within a rigid code-based structure. But researchers are definitely framing these as challenges for future refinement, absolutely not as permanent roadblocks. Which brings us to our final provocative thought. What are the implications of AI models that can actively write, execute, and simulate their own code to solve complex problems? We are quite literally looking at a future where AI systems don't just guess the next word, they actually build and execute entire logical frameworks on the fly, substituting human-like intuition whenever the raw math runs out. Thank you so much for joining me on this explainer, and I really hope this leaves you eager to explore the fascinating future of AI prompting.